Nice.
Well, if I don't change it after, we'll see. but actual science is my target.
Okay. Do you have to go to Calc 2?
Yes, all the way until Calc 3.
Yes.
I was going to say, stick with the professor. You might be okay.
Yes, yeah, that's what the other day he was talking about, like for the fall, he might change to Calculus 3. I'm like,
I know. I don't know.
Don't do that.
Well, it depends on like how selfish I am. That's the thing.
Okay.
Because I already have all that stuff prepared, you know? Like, that's the only thing. Like, how stressful do I want my summer to be? So it really depends on how much I care about you. The decision point, like.
Because when I saw your name the other day, they were like, yes, finally, I don't have to switch professor anymore.
Right. I know. You get comfortable and you're like, yeah.
But we'll see.
It's nice sticking with the same teaching style.
Yeah.
Yeah, you definitely get comfortable with that. Just getting.
How was your birthday? Did you do anything fun?
Nothing fun at all.
Oh.
Just hanging out with family. It was good. I hung out with some friends this weekend when it was a little bit nicer. So that was nice.
Like you didn't play Xbox with the boys?
No. No.
Oh, here, you'd actually appreciate this. So this is big. I'll see if I can show the camera. This is Big Brother issues.
Nice.
The next step's going to be that second controller just not plugged in, but.
Right.
It made me laugh. I walked in and she's sitting on. We have it set up at the guest bedroom so it's not disturbing everybody. And we did the same thing where it's like she's sitting in his lap and she's got her remote control and he's playing like it's like Minecraft or something.
Yeah.
And totally loved it. Oh, I know you wanted to be seen. You were not helping me here. Oh, there. Happy now?
Hi.
She has got to be the center of attention.
Of course. Naturally. Wait, I don't think we said, did we say a time? No, we didn't say a time, did we?
For?
The final exam due. I think that was for one of my other classes.
You just said you'd post it after Tuesday's class and it would be due by midnight on Wednesday.
Yep. There we go. All right. I think that's the plan. Let's see here. Get the chat window up.
Yeah, you do not need coffee. I don't think so.
Maybe only once. Like, oh.
I don't think she's tried. She eats, so I'd be nervous. Like
she might actually like it.
She's like, yes. Oh, like, no.
That's funny.
You already zoom around in your walker. I don't know.
Right. She doesn't need any more caffeine. Any caffeine at all.
Like pulling the dead out of the grave, and then this one, she's up in the morning. She's like, let's play. It's like, oh, okay, hang on.
Right. Yeah, my oldest gets up. Like he got up at like 5 for a long time until he was 2.5. He had his like adenoids were swollen, like so he would like kind of and like snort himself awake. So he would wake up super early. So we got those out and that helped him sleep a little bit. Now we like have to tell him like, don't get up before 7. 7, please.
My oldest was that way. We did the old-fashioned face clock, and I color coordinated it. And I was like, "Do not wake up and get out of bed until."
Nice.
He did the same thing. It was like 5, 6 o'clock in the morning, and now she's 5. She wakes up at between 4 and 4:30 every morning.
Okay.
And my oldest, it's like 7:30, and he's like, "I'm still tired." I'm like, table to parents. Like, you need to get up. You've got class.
Yeah. All right, I think it's time for us to get going here. We're short enough left where I can just like list the final things coming up on one sheet here. So we have one last quiz this Thursday. We're gonna have a special Monday class next week because that's our last week. So Monday, we'll do more examples, do some 5.5 examples. Tuesday will be review. We can do more examples, whatever you want from there. And then after class on Tuesday, the final will be posted, and then it'll be due by the end of the day on Wednesday. Yeah, any questions about the timeline coming up for the last week here? All right, we're not seeing any. Let's see, always make sure I'm recording. Yep, recording. Okay. I do have some other spare time. Like if you have specific questions you wanted to go over, you can always email me, or we can schedule a Zoom conference if that would be helpful, especially on some of the stuff near the end. You know, if you feel like the sessions aren't enough and you still have some questions, just let me know. In fact, like today is one of my extra days where I'm available, right? Yeah. So I'm available until noon today if you wanted to just shoot me an email, or maybe sometimes lately we've been hanging out after class a little bit, so that works out too. Today, let's start with the quiz. You should see feedback written in D2L in the Dropbox. So let's go over that quiz. Let me pull that up here. Quiz 10. I feel like this quiz was the first time we were really seeing the effects of like kind of rushing and exhaustion at the end of the semester and not getting good in-person instruction. I really, like, this was the first one where I really noticed, like, if you had some big gaps in understanding and like you didn't really know what to do, you are not alone. And I noticed quite a few people with that. So I would encourage you. We're going to see these questions again on the final. So I would encourage you, if there are things you really don't understand about these rectangles and the lower sum and upper sum and Riemann sum and all this stuff, we could probably fix it in like 10-minute one-on-one chat. So I would encourage you, if you're still struggling after this, reach out and we can probably clear that up. The first question, we're supposed to approximate the area under the graph of tangent of x from 0 to pi over 4 using the upper sum and 4 subintervals. So you'll see I have my drawing over here on the left. I think that's super valuable, whether you graph it yourself or you graph it on Desmos, whatever you need to do to get a sketch. Make sure you know what the graph looks like, especially if you're looking for a specific upper or lower sum, because you have to make sure your upper sum, all your rectangles are above the graph. That happens to be right endpoints here. If you look in that first interval, 0 to pi over 16, the right endpoint will give you, all of them will be above, they'll all be above the graph. So you're going to use the right endpoint. When I mean use the right endpoint, you're going to use the right endpoint to get the height. So you put that right endpoint into the function to get the height of that rectangle. And that's what you'll see when I have my notation here. F of pi over 16, that's the height. And then F of pi over 8, F of 3 pi over 16, and F of pi over 4. And the width of each one is pi over 16. I just kind of did that in my head. The whole interval is pi over 4, so fourths. And if you cut it into 4 subintervals, it would be 16ths, so pi over 16. Then I used Desmos to do that. Pi over 16, they all have a pi over 16, so I just factored it out, pi over 16. So it's tangent of pi over 16, tangent of pi over 8, tangent of 3 pi over 16. I just put 1 here because tangent of pi over 4 is 1. And you get a decimal approximation. Some people don't know what hundredths are. Hundredths is 2 decimal places. Quite a few people put 3. It's okay. I didn't have any deduction for that, but hundredths would just be 2. So that's the first one. Second one, I think people did pretty well on this one. It's just like, what does this notation mean? So you're going to write it as an integral. And to do an integral, you need 2 things. Well, maybe 3. You need to know what is the function. You need to know what the variable is. And then you also need to know the bounds for that definite integral. So when in the Riemann sum, it has to give you the interval, and that interval becomes the bounds, the lower and upper bounds. You'll see I put this notation here, the cosine of u sub I sine plus sine of u sub I, that is the function. That's the height. You put u sub I into that function to get the height of those rectangles. So that is the function itself. And so you simply make it cosine of x plus sine of x. And I said you had to know the variable. It really doesn't matter what letter you use there. I could have done any letter. So I could pick a variable, I don't know, g, integral 0 to 2 pi. This is a really weird one. I've never seen this. Cosine g plus sine g dg. It's just a letter. It doesn't matter the letter. But some people had like u's and x's. You have to have the same letter. It has to be the same letter. This function must be a function of the same variable that you're integrating with respect to. So those need to match. And a couple people didn't match those. Okay, we have to do the back still. Any questions on the first two problems from the quiz so far? All right, let's look at the back. Number 3, we're expressing the shaded area as a definite integral. This one people did really well. The area is just the area. To get the area under a curve, if the function is positive, to get the area, you just integrate. And this one starts at 1, ends at 6. So those are the bounds in the integral from 1 to 6. The last one was a little more challenging for people. Also, I mean, overall, we did pretty well. But there's still some misunderstanding of area and integral. We kind of overlap them and think the integral, the definite integral is the area, but that's only true if the function is positive. So it is totally acceptable to have a negative integral. And it's all about like, what do these, like, because we're kind of misinterpreting, maybe it's an explanation about that, those rectangles. So this one,
last part about it's only true if, because you kind of broke out on my side.
Sure. So the definite integral is only the area if the function is a positive function. So for example, 3, this function is entirely positive. So then the integral from 1 to 6 will be the area under the curve. But let's say, let me go over to, so I don't want to screw up this too much here. Let me just go over to some blank workspace here. Let's suppose we had a function that looks something like this. Oh, we could do like sine or cosine. Let me do cosine. I feel like we talked about this. Maybe, can't remember. So here's cosine. And we have these two areas. One is above the x-axis, one is below the x-axis. In fact, if we took the integral from 0 to pi of cosine of x dx, in fact, we would get 0. But that's, of course, not the area. The reason is if you think of the rectangles, when you're putting these values into the function, here this f of u sub I, whatever that is a positive number. The function is a positive number, so it represents area, because the function is positive, so it's like a height. But when the function becomes negative, here, whatever this u sub I would be, here this f of u sub I is some negative number. So the integral is not necessarily always area. And that's a little confusing. We kind of use area to explain the meaning for it and look at these rectangles. And if we add up the area of all these rectangles, we get the definite integral. If we're a little more precise about it, the definite integral is really summing up the function values times the width, and the function values can be negative. So that came into play in the quiz for number 4, because indeed using left endpoints, right? We were supposed to use left endpoints. We were supposed to go from 1 to 9. And the function started at 9 and went down Because let's see, it is 9 minus x squared. So when x is 0, it's 9. And then when x is 9, it is 81. 9 minus 81, that's the negative 72. So if we use left endpoints, we have at 1, and at 3, it's actually 0. At 5, it's negative, and at 7, it's negative. So these two rectangles, we're not actually in when we're finding the Riemann sum and approximating it with this partitioning, they're actually going to be negative numbers because we're not going to find the area. We're actually using the function value. They're actually going to be negative. So that's why you should end up with a negative number here for the approximation for that definite integral. All right, I think that's it from the quiz. Are there any questions on the second page, numbers 3 and 4?
I have a question about the cosine function that you just did. When I plugged that into the my calculator, I didn't get 0. I got a negative 3.2 times 10 to the negative 14.
Yeah, so it's because your calculator is not as good as we are. And it's doing a lot of small rectangles and computing them and grinding them out. If negative 3.2 times 10 to the negative 14th is negative 0.000000000000032.
You would just take the 0 instead of all of that.
Well, so your calculator is not as smart as you. Your calculator is just grinding out and doing a bunch of computations and then adding them all up, and it's rounding. So we know how to do this definite integral. We actually know how to do it now. That's the fundamental theorem of calculus. I feel like we did this one last time, where that's the antiderivative of cosine. What's the antiderivative of cosine?
Sine, negative sine.
Oh, you had it right the first time. It's super easy to mix up. The derivative of sine is positive cosine. So the antiderivative of cosine is positive sine. Super easy to mix those up because we've been thinking derivative for the last 2 months. And now we're like switching directions on you. So it's really, don't feel bad. And then we're going to evaluate that from 0 to pi. So that's sine of pi minus sine of 0, which is 0 minus 0. So we're smarter than the calculator. The calculator is actually doing rectangles and adding them, just doing a lot of them and adding them all up. And it just rounded, not quite as precisely as we are. Any other questions from the quiz? All right, let me know if you have any. You should be able to log into the Dropbox and see my comments written right there on the quiz. It's easier to do that. For exams, I'm going to download them and write my comments there. Let's see here. What is up for today? So we got to do some homework questions. I have extra practice from 5.3. We just did a couple at the end of class on Thursday. So hopefully we'll have some time today to do more of those. And then I have some 5.4, a couple of examples as well from 5.4 if we need them. But let's do some homework questions. Let me pull up the homework here. So let's start with 5.3. Are there any questions from section 5.3?
25.
All right, sounds good. Let me get in here. Should have had this ready. Let's see. Integral 5.3. Number 25. All right, so we're doing the fundamental theorem of calculus here, where we're going to need to find the antiderivative. And this is where you're going to want to have some good notes. Remind yourself all these derivatives. So I'm going to write down the derivatives of the trig functions here, just to remind us. And then we're of course doing the antiderivative. Whoops. So it's not sine or cosine. We have the derivative of tangent is secant squared, so it's not that, but we're getting closer. The derivative of secant of x is secant of x tangent of x, that's not it. The derivative of cotangent of x, now this is going to be close, is negative cosecant squared. So that's got to be it. It's got to be some version of that. And the derivative of cosecant is negative cosecant cotangent. So it's clearly some version of the cotangent. So if the derivative of the cotangent is negative cosecant, you could almost think of it this way. The derivative of the cotangent of x is negative cosecant squared. And so why don't we just multiply both sides by a negative? So this means that the derivative of negative cotangent of x must be positive cosecant squared. So that means the antiderivative of cosecant squared is actually negative cotangent. And then we're going to evaluate it from pi over 6 to pi over 2. For me, even now, I still always kind of check these in my head and kind of cover up. I can't really do it. Like I can do it with my finger, but you can't tell. Like cover up the negative sign. And so the derivative of a cotangent is negative cosecant squared. So I need this negative here so I can get a positive in the integrand because this is the derivative. What you're integrating is the derivative. Oops, I just like opened up some other software with my wrist somehow. Okay, and so now we need to evaluate this at, I'm going to do it this way, negative cotangent of pi over 2 minus cotangent of pi over 6. Are you okay from here, Christopher, or do you want to keep going? Did you find your, like, where you got stuck?
Could you finish it off?
Yeah, sure. Yeah, no problem. Cotangent of pi over 2. Pi over 2 is, well, let's see. Pi over 2 is right here. Cotangent is cosine over sine. So that would be 0 over 1. And then cotangent of pi over 6, that's over here, 30 degrees. Maybe we can do the sides of the triangle. 1, 2, square root of 3. Tangent would be opposite over adjacent. So this one would be adjacent over opposite. Square root of 3 over 1. And so it looks like we get square root of 3.
Thank you.
Yeah, no problem. The biggest challenge for this last unit for most students is like rewiring your brain a little bit because you have to work in reverse. Because now you kind of want to, you're going backwards to find out the antiderivative. What's the function whose derivative is the thing you have? So it's kind of, it takes some practice. So that's 25 from 5.3. What other requests are there?
Question. When I plug that into the calculator, it's not coming out to anything. It's coming out as an error.
I don't know what to tell you. I mean, I could open up my calculator. We could try to mimic it. let's see.
Would it be
here.
better to do these trigonometric functions with by hand?
You should get the same answer. So something's getting mixed up there. So do you mean, like, did you do the integral or evaluating the cotangent at the end there?
Evaluating at the end.
Yeah.
I did 1 over tangent pi over 2 minus 1 over tangent pi over 6, and I have an error.
Well, tangent of pi over 2 is not defined. You can't take the tangent of pi over 2. That's the problem. Tangent of pi over 2 is a vertical asymptote on tangent. So I understand what you're saying. When you're using this, when you're saying cotangent of x is 1 over tangent of x, that's only true if tangent of x is defined. And so tangent of pi over 2 is not defined. Whoa, I like lost my focus. Oh, that was weird. Tangent of pi over 2 is not defined, so you can't do that reciprocal identity. There should be a cotangent somewhere in here. Maybe in the math menu. Oops, just quit. I don't know. I feel like there's a cotangent in here somewhere. Maybe in the catalog. Where do you get to the catalog? Oh, I don't want to scroll down that far. But there might be a cotangent. I mean, I think this is kind of pointing to, nope, no cotangent. The value in, I mean, there's no reason why the calculator couldn't do it. I bet if you did it in Desmos, it would do it. But we should really be able to do that too. You know, we should be able to compute those. Let me see if I can do it in here. Cotangent of pi over 2 minus cotangent of pi over 6. And actually it was the negative of this, but nope, this calculator doesn't have it. Okay, let's try the other Desmos one, the main graphing one. I think that one has it. I don't know why I wouldn't have it over there. Cotangent of pi over 2. Oops, cotangent of. Yeah, see, so here it can do it. But this really took like 3 times as long. And then I don't know what that number is. That's not the exact answer. So you could use it to check your work, but you're still going to need to do it by hand to get that exact square root of 3. Yeah, so that was just a calculator thing. It looks like you had the right idea. And then the problem with the reciprocal identity is if tangent of x isn't defined, then doing 1 over it doesn't work. All right, any other homework questions?
I have a question. It's not about the homework. I apologize. Are
That's
we going to
okay.
be allowed to do Desmos on the final to double check our answers like we've been doing with our quizzes?
Yeah, that's good. I think that's a good tool. And I would love to have it in our regular classes. And in the future, I was thinking about it, like I might just screw it, let people use their phones and just kind of make sure that they're only using that app. And, you know, because it's a super useful tool. And it's something that like it can almost give you extra insights. And it's not just like proving that you're right. You can do cool stuff with it that you wouldn't otherwise be able to do. So, yep. So I'm going to consider it an allowable tool. Yeah. All right. Could you say that one again, Christopher?
I was going to say, could you go over 43?
43, sure. Let's see here. So this one is a bit of, we didn't do any of these examples on Thursday. We focused on the other part of the fundamental theorem of calculus. So my guess is that there's like, what is this accumulation function? Find f at the given numbers, graph f. So here's the idea. We're going to graph our original lowercase f of t from 0 to 4 pi over 3. This is t. This is our f of t. Cosine starts at 1 and goes down to -1 at pi, and then starts to come back up. It crosses again at 3 pi over 2, and so 4 pi over 3 is somewhere it's less than that. And what this accumulation function is, we're kind of adding up, so it's the integral, but it's a function of x. So what we're going to do is we're going to put an x here just as a drawing. I'm just going to label the x there. That's just as an example. And the accumulation function, capital F of x, is the integral from 0 up to x of this cosine of t dt function. So it is the integral from 0 up to that x of the cosine of t function. That's this accumulation function. So that's part A. Then part B, you would just evaluate the integral. So you can see here, we know the antiderivative of cosine. We did that already. That's sine of t. And that's sine of t from 0 to x. And so it's just going to be sine of x minus sine of 0. And sine of 0 is 0. So it's just going to be sine of whatever that value is. So f of pi over 2 will be sine of pi over 2, which is 1. Or sorry, I did out of order. I'm sorry. Pi over 6 was the first one. F of pi over 6 will be sine of pi over 6. And let's see here. Sine of pi over 6, 1/2. And then f of pi over 2, sine of pi over 2 will be 1. And f of 4 pi over 3, sine of 4 pi over 3. Anybody know that one offhand?
Negative square root of 3 divided by 2.
Nice. Thank you, Haley. Negative square root of 3 over 2. So 4 pi over 3 is over here. That interior angle there is 60. So this is negative square root of 3, -1, 2 for the 30, 60, 90. That's one way to do it, is to use the triangle. And then part C is to graph our function, graph our accumulation function. And the accumulation function is just sine of x. So I guess we should stop it at 4 pi over 3. So something like that. Now this is kind of interesting here. This is the accumulation function, which seems like it's accumulating. We think of that word accumulating, getting bigger and bigger and bigger. And the accumulation function does get bigger for a while. But then at pi over 2, for some reason, the accumulation function starts getting smaller. So why does the accumulation function, which is supposed to be adding up, why does the accumulation function start to get smaller at pi over 2? This is related to something we were talking about earlier. There's a good reason why it starts to get smaller at pi over 2. I'll give you a hint here. Here's pi over 2 in red.
Is it because it's getting closer to 0?
Could you specify the it?
The because the graph or the what we're looking for is getting smaller and getting closer to 0. So like the area at that point.
Right, the area, we're not adding much area at that point. So at pi over 2, we're not adding much area, and then look what happens after pi over 2. Now it's getting negative. So we're actually kind of losing area. This is the thing we were talking about earlier. When the function goes below the axis, the integral actually starts to become negative. So now we start losing area, and then by the time we get to pi, we've lost all the area we gained before pi over 2. And so it's down to 0. Because the area above and below are equal and you get 0. And then it's more negative after that. So it continues to be negative. So that is 43. Christopher, this was your question. Does that clarify the questions you had?
Yes, it does.
Okay. Did anyone have additional questions on 43? All right, we have a request from 5.4 from Haley. All right, 5.4. We have not done anything of this with us together in class. We did post some videos, but we haven't done anything together. It takes a while to load like all the equations and stuff. I don't know if I think they're images. Loading 25. What are we supposed to do here? Find each definite integral using the fundamental theorem of calculus and properties of the definite integral. All right. 25. So the issue with this one is we can't really just jump in and use the fundamental theorem of calculus right now because you don't know a function whose derivative is x minus 1 times x plus 3. Like, you can't just jump in and do that. So the properties that I believe we are intended to use here, let's scroll up back into the textbook here. Just minimize this, there we go. So there should be some properties up here. This is average value, mean value theorem, blah, blah, blah. Where are the properties? Should be coming up here toward the beginning. First of all, if you have, oh, not that one. That one's not going to help us. If you have a sum of some functions, you can find the antiderivative, you can find the integrals separately. And then if you have constants times functions, the constants can come out. So this is what we're going to use, and this is really valuable for polynomials, which is essentially what problem 25 is. So the way we're going to do this is we're going to actually do some algebra first and just multiply out those two binomials and get x squared. We'll get a 3x minus 1x is 2x minus 3 dx. Now you probably don't remember because it's just like obvious now, but when we first introduced derivatives, I actually took the time and separated and wrote each term separately and like pulled constants out. So you can do that same thing with integrals, but I will tell you eventually you will not do that. But what they're telling us is that this should be equal to the integral from -2 to 3 of x squared dx plus the integral from -2 to 3 of 2x dx minus the integral from -2 to 3 of 3 dx. You should be able to do the antiderivative of each of the terms. Now, for me personally, I typically will do them all at once and not write these individual steps. Just like you, if I asked you to take the derivative of x cubed plus 4x minus 2, you would just, in your head, take the derivative of x cubed, take the derivative of 4x, take the derivative of 2. You would just, in your head, do that. You wouldn't actually rewrite the derivative of each term. And so this step that I just did, like to these next couple steps, I would encourage you to, by the time you get to the quiz on Thursday, you're not actually writing these 2 steps. I'll show you what I would recommend that you get to. But now we can do the power rule here. This is the reverse of the derivative power rule though now. Now we're not multiplying down and subtracting. Now we're adding and then dividing by that new exponent from -2 to 3. The 2x is actually set up nice. You could put the 2 out in front and do the power rule again, but it already is the derivative of x squared. The derivative of x squared is 2x, so the antiderivative of 2x is x squared. What about the last one? What's the antiderivative of 3?
3x.
Yeah, it's 3x. Remember, when you take the derivative with an x there, you just lose the x. And then we can compute each of these. I'm going to show you, there's like 3 steps that I would combine into one to make this more efficient, but I'm going to keep doing it this way for now just to illustrate. 3 cubed over 3 minus -2 cubed over 3 plus 3 squared minus -2 squared minus 3 times 3 minus 3 times -2. And then it's just kind of tedious from there, but you're just doing these computations. 9 plus 8/3 plus 9 minus 4 minus, look all these 9s, 9 plus 6. So 9 minus 4 is 5. 9 plus 6 is 15. 9 plus 5 is 14. Minus 15 is -1. -1 plus 8/3. And then -1 would be -3/3, so 5/3. So that's what they meant there by using the properties of definite integrals, where you can take the definite integral of each term. I want to show you a slightly different way to do it, but Haley, does this answer your question?
Yes, I wrote the problem down wrong. I wrote it from 1 to 3 instead of
That's the worst.
-2.
And 1 to 3 would have been better than no negatives. That would have been easier. Maybe your brain was like, I don't want to do any negatives. I'm just going to change it to 1. Oh, man. So let me, oh, sorry, go ahead.
The integral of the sum of 2 functions, does that also apply to subtraction?
Yeah, because the sum, a minus b is really just a plus -b. It's still a sum. So, yep. Yeah, so I'll tell you how I do this. I would go right from here and just kind of mentally take the antiderivative of each term, x cubed over 3 plus x squared minus 3x, and just have one big function evaluated from -2 to 3. That's how I usually do it. You get exactly the same answer. To me, these steps get a little cluttered to me. Actually, all 4 of those. All 4 of these, they just get a little cluttered to me. A lot of that's personal preference. It doesn't matter. You get the right answer either way. But I like to put all of the 3's in and then subtract all the -2's. -2 cubed over 3, -2 squared, minus 3 times negative 2. And so I like to do it as one big polynomial function rather than each individual one and doing the lower and upper. But like I said, it's really personal preference because it doesn't give you a different answer. It gives you exactly the same answer. So it's totally up to you. Right. So that's one property of definite integrals is you can take the integral of each of the terms in an integral like that, each of the functions. Okay, what else? What other homework questions?
Can you go over 63C from 5.3?
Haley, is yours from 5.4? The 39 that you put there?
Yes, from 5.4.
Okay, it was a quick draw. And since we're already in 5.4, I'm going to do Haley's first. Then I don't have to click over to 5.3. So remind me, Christopher, you said 63C?
Yes.
All right, we'll do that one next. We'll do 39 here. Aha, okay. This one, a graph will be really helpful. Oh, shrunk it down too much there. This one, if you recall, is called a piecewise defined function, where you have your function given to you in two pieces. And so let's graph it. We're looking from -2 to 2. And we have 3x when x is negative. So that'll be, let's see, I guess we would leave off 0, 0, because 0 is not included. And then when x is -1, it'll be -3. And then when x is -2, it'll be -6. I don't know if going by 3s will work for the other half, but we're committed to it now. So on the right side, it's 2x squared. All right, and then 0 is included there, so when x is 0, the function will be 0, so that fills in our hole. That's fine. And then when x is 1, it'll be 2. And when x is 2, when x is 2, 2 squared is 4, times 2 is 8. So this looks like a line. My graph is off. It's definitely a parabola, right? It should be a parabola. It looks like a line just because my drawing is not great. Incidentally, you can graph this in Desmos. Watch this. You can graph y equals 3x, and the way you do the pieces is you put a brace 0 less than or equal to x -2 less than or equal to x less than 0. And then y equals 2x squared 0 less than or equal to x less than or equal to 2. And there you have it. So you can graph piecewise functions pretty easily in Desmos. You just tag on in braces what the restriction is for the x values. Okay, so we want to find the integral. And this is, again, it's similar to, it's one of the other properties. If we scroll back up to the properties, there's another property that says you can break up an integral. Here it is. I don't know what page this is on if you're using your actual book, but you can, if you want to go from A to B and then C is in between, you can go from A to C and then from C to B. That's what we're going to use here. So we're using this, if I have the integral from A to B, and I want to find this integral, I can, if I want, go from A to C and then add from C to B. And that's what we're going to do on 39. The integral of f of x dx from -2 to 2 is going to be the integral from -2 to 0 of f of x dx plus the integral from 0 to 2 of f of x dx. And then we'll use the two pieces. So it's -2 to 0 of 3x dx plus the integral from 0 to 2 of 2x squared dx, because those are the two pieces. It's like too small. So how's that, Haley? Does that answer what you needed there?
I'm just confused at which numbers to plug in to the antiderivative. Would you plug in -2 and 2?
No, you're gonna do, now, do you see where I am right here? Like,
Yeah.
you're gonna do those separately. Like, treat them each as their own problem. So
Okay.
if you just kind of split it up, you're gonna do them separately. So this would be 3x squared over 2 from -2 to 0. And this one would be 2x cubed over 3 from 0 to 2.
Oh, okay. Thank you.
You're splitting it up as two separate integrals, and then you just do them, whatever they say. Just kind of follow their lead.
Okay.
Mm-hmm. All right, let me go back to 5.3 now. We'll hit up that 63. I know as a student, sometimes you can feel like these problems at the end are like, oh man, these are just like the hard problems to kind of really challenge you. And I would encourage you, like, I'm really glad that Christopher asked about this, because if I'm going to be honest, these problems at the end are really the whole point. It's easier to introduce the idea of definite integrals with functions and finding the area under the curve, but I can assure you, no one who's using integrals is out there finding areas under curves. There's always some context, some meaning. What does the function represent? But now I might be computing the definite integral, but it represents something. It's not just area under a curve. So this problem is really the whole point. This is a really good one to talk about. Now I know you asked about C, but I kind of want to talk about A and B also for everybody else. So this is a colony of bacteria. Bacteria does grow exponentially, at least until they run out of food, and then they all die. So bacteria growth for a while will grow exponentially. And that's what this is. This is an exponential growth. That's actually its growth rate. That's not the population, but that's the growth rate. Notice it's kind of hard to see on the ebook, but there's a prime there. That's B prime for the amount of bacteria. So letter A is find the definite integral from 0 to 6 of B prime of t dt, which will be the integral from 0 to 6 of 3.455 times 1.259 to the t dt. And you should have somewhere a formula for the antiderivative of exponential functions. The 3.455 is just a constant, so it can just be multiplied by this. So you can, the 3.455 can be pulled out of the integral. Just like you would with derivatives, you can take the derivative out in front, or take the constant out in front. So let me put over to the side here, the derivative of, how did we do it? Did we do like a, we did a, let's do derivative with respect to x of a to the x. Does anyone remember that one? Exponential derivatives, the derivative of a to the x.
I'm trying to figure that out. When a to the x times. Oh.
You're still there. You're there. So if we're taking the derivative with respect to x, yeah, it would be natural log of a times a to the x. So that was good. That was good memory there. Yep. So we're going to do the antiderivative now. And so what you could do for the antiderivative is basically divide both sides by natural log of a, because that's just a constant. Okay, so the integral of a to the x dx is a to the x over natural log of a. Basically, you do the opposite of what you did in the derivative. If when you took the derivative, you multiply by the natural log of a, well, then in the antiderivative, you're going to divide by the natural log of a. You're doing it in the opposite order, just like the power rule. Instead of multiplying in front and subtracting one from the exponent, now you're adding one to the exponent and dividing. You see what I mean about how easy it is to get mixed up? Because you're like reversing directions. So it's totally normal. And you will probably not be completely comfortable until you've taken Calc 2 and gone in like a month into Calc 2. And you start doing it often enough, and then your brain is like able to do either one. It reminds me, I watched this video of this Smarter Every Day. It's like a YouTube channel. He does some cool videos. And he did this one where he made a bike, or a friend of his made a bike, but he put in 2 gears, and so the handlebars reversed. So like turning the handlebars left made you go right. And it took him, he described, it took him like months of practice to like, finally he rewired his brain and so he could ride this crazy bike where the handlebars were switched. But then he went back to the first one, the regular bike, and like his brain had like, wait a minute, and it like took him a while, but eventually he got practiced enough where he could do either one. And that's kind of where we are right now. Right now we're just messing with you because we're learning the opposite way now. And hopefully you won't lose what you remember about derivatives. And it isn't really until Calc 2 when you're doing both intermixed with each other that you really get comfortable. So my point about that long tangent was to encourage you, if you're feeling a little confused and you're mixing them up, it's a very common progression. Be patient with yourself. Don't get too frustrated. And it's a very normal thing to feel. So back to this example, this means it would be 1.259 to the t divided by the natural log of 1.259, evaluated from 0 to 6. And that's just a calculator problem. I'll let you do that on your own time. That's not the interesting part here. So B and C are the interesting parts. So the interesting part here is, what does this actually represent? So this is something we didn't talk about. I had it in my 5.3 examples. We kind of briefly talked about it at the end, I think. Maybe not. It's this net change. So where we go? Well, when you integrate a rate of change, which is what B prime of t is, it's a rate of change. When you integrate a rate of change, you get the total net change in that quantity. That's what the definite integral represents. The integral of a rate of change gets you the net change in the function. So here I'm doing the rate of change of the population. So I'm getting the net change in, I guess I could do, let's use words here, the net change in the population of bacteria.
Quick question.
Yes.
So the B prime of T was giving you the rate of change per hour of how much it was growing. And then the net change is exactly what it is at that hour, at 6 hours, right?
Close. It's not what the population is. It's what the change in population is exact after the end of 6 hours.
Okay, so how much it's grown.
Yes.
Okay.
Yes. So it's the growth in the number, let's really flesh this out here. It's growth in the number of bacteria after 6 hours. That doesn't even look like horse. Hours. It's the growth in the number of bacteria. And I know it's growth here, by the way. Does anyone know, besides the fact that it's bacteria, do you know how I know that it's growth? Because yeah, I guess you could have bacteria dying.
Is it because the numbers are positive?
Yeah, exactly. Yep. So because we got a positive answer, that means we're getting more bacteria. Yep. So that sign is important here. This is where, remember, we're talking about area, and area, like the integral isn't always positive. Sometimes you can have negative ones. And that would be like, if your rate of change of bacteria is negative, you're losing bacteria, then your net change would be negative. Your integral would be negative, and that's totally possible. They definitely get some integrals that are negative.
So the growth would be so if it was negative, it would be how much it has died.
Okay. Yep. Yeah, it's technically net change, and that net change can be positive or negative. Yeah, Lorenzo.
So I had a question with the where it's a B prime of F dt.
Oh, that's T. It
Oh,
looks
okay.
like it
Yeah.
totally looks like an F.
Okay, then that fixes a lot. I was wondering because I was like,
what?
yeah.
That's I'm gonna blame it on the pen. It's the pen. It's harder to write on here.
Yeah, I bet.
Yeah, you're looking at it, you're like, dude, that looks exactly like your penmanship on paper. Yeah. So Christopher, now with this discussion, do you think, let me scroll up so everyone can see what C is. If 15 grams of bacteria are present at T equals 0, how many grams of bacteria are present after 6 hours? Do you think you can answer that one now? Sorry, I cut you off.
So you would just add that amount that you just got.
Yeah, exactly.
I was confused on where the 15 would be the start of, but
Yes.
you would only find what 15 was after you do B.
Yeah, the 15 is just like a constant that you're just going to add on. You have to do B. So 15 grams initially. So after 6 hours, the population would be, or like, well, not population. I mean, I guess it is population, but the number of bacteria would be equal to 15 plus, like you said, whatever you get from part B. So I can guarantee that on Thursday's, either on Thursday's quiz or on the final or both, you are going to be asked a question like letter B. Because it's great, like you definitely have outcomes from this course are that you can do a definite integral. You'll have definite integrals also. So I want you to do the definite integrals. Yes, so letter A, you'll see letter A also. But letter B is crucial, that if you have a context that you know what the definite integral means. And if you can just remind yourself the integral from A to B of a rate of change is the net change. And then of course you have to flesh it out and kind of explain the context. And if I have a definite integral and I ask you to explain what it means and you just tell me it's the net change, you're going to get 0, because that just means maybe 1 because you had something good on your formula sheet. But you got to actually explain what it means in the context. So these words that I wrote here, either one of these would be fine. It's the net change in the population of bacteria, or it's the growth in the number of bacteria after 6 hours. The second one is better, but the first one is okay. So I'm really glad that you asked. Yeah, Haley.
So for part C, it said you would add 15 plus your answer from part B, but wouldn't you add the answer from part A? Because I thought part B was just an interpretation.
Yeah, part A.
Okay.
It's
I just wanted
Christopher's
to make
fault.
sure.
Christopher, let the record show he said part B. Just the record show. We can replay it. This is in YouTube. That's fine. You're right. So whatever the number we got. Yeah. You know, everybody knew what we meant. It's fine. Good catch, though. Good clarification. All right. So I'm really glad we brought this one up. This is an important topic. While we're talking about it, let me jump over. I know you might have some more homework questions. Well, actually, it's 10:32. So just before we end the class, let me jump over and to the 5.3 extra examples, because we're right on this topic. And let's do like a couple more quick ones here just to talk about this, because it's such an important idea. So again, this is the other textbook we used to use. I don't know if your textbook calls it this. I think they do. Where is it? I can't remember. I feel like I saw it in here somewhere. It might be in. I'm not going to be able to find it quickly. So we're going to call it the net change theorem. The definite integral of a rate of change gives the total change or net change in that quantity. So the integral from A to B of, we'll call it f prime of t dt, is f at B minus f at A, which is the net change in the function f. And this f prime of t, it's a prime, right? And it's a function of t, so it is a rate of change. So the definite integral of a rate of change, not f prime of x, but a function of f prime of t, time. So it's some rate of change over time, gets you the net change in that function. So a couple of just like theoretical examples. Suppose p prime of t represents the rate of population growth of Elgin t years after 2005. So p prime is the rate of change of the population. So what would that definite integral represent? Well, it would be a net change. And the net change in what?
In population growth of Elgin in 5 years?
And specifically, yeah, between 2005 and 2010, right? So I'm going to word it the net change in the population of Elgin between 2005 and 2010. You said the net change in population growth. I think it would be better to do either the net change in population or the population growth of Elgin, etc. I get a little nervous with using growth here. I think it's safe because I think the population of Elgin was growing then. If we don't know that it's growth, it's better to just use net change because then it accounts for a negative. Yeah. All right, and then the last one here, if v of t represents velocity is the rate of change of position. So if you did a definite integral, you would get the net change in position. And if we want to be really precise, between t equal a and t equal b, whatever those are, we don't know what they are here. They're just a and b. And then last question for you. If you have to go, it's 10:37. So if you have to go, it's fine. This is again that question about positive integrals. Is the integral above always positive? Why or why not? Under what conditions might it be negative?
Would the answer be no? It's not always positive.
Okay, you're correct. Do you have a thought about why?
When something's slowing down.
Ooh, good thought. If it's slowing down though, the velocity is still positive. So it's still moving forward. So it would still have a positive change in position.
Would it be when it's going backwards?
Correct, right. Then it would have negative velocity, and its change in position could be negative. It could end up backwards from where it started. Yeah. Yep. So v of t could be negative. So it could move backwards. And again, just as I like that idea there to just tie into this idea that definite integrals can absolutely be positive or zero or negative. Those are all possible, and they have different meanings then if they are. All right, I'm going to stop the recording now and let class officially end. I think I should probably do announcements for people who aren't here. So just a reminder, yep, I'm still here. Yep, there you are. For Thursday, we have one last section of videos to watch, 5.5. For those who are finishing in Calc 1, and this is your last calculus course, this is just another section. It's 1 or 2 problems on the final. For those that are going on to Calc 2, this is the most important section in Chapter 5. And in Calc 2, your instructors will know that this was a crazy semester and they'll review it, but you'll be ahead of the game if you really work hard. And I know you're tired and it's like a lot going on and we have 1 week, but it's really going to be valuable for you to spend time doing that. So Thursday, we'll go over questions, probably focusing on 5.3 and 5.4 because we have our last quiz. Monday, we're going to have an extra meeting. We'll go over 5.5 questions. Tuesday, we'll do some more review. And then the final exam will be posted after class on Tuesday. That is not a lot of review time. We lost a week, right? And so it's not a lot of review time. I would encourage you to reach out if you have questions. I'm happy to meet with you one-on-one or reply via email. Devontae, question before we close out the day?
Is the exam reflection due today?
Oh, yes, I forgot about that, right? We had midnight tonight as the deadline for the reflection, right? Yep, May 5th, that's today. So yeah, yep, exam reflection due tonight. Yep, thank you for bringing that up.
No, of course.
All right, I'm gonna end the recording